In this video, we're going to look at graphs of tangent functions. We're going to generate a graph of a tangent graph from the unit circle, and then we're going to identify some of the properties of the tangent graph, such as its period, the periodicity of the graph, and we're going to talk about the fact that the asymptotes are used to show the behaviour of the graph. They're not actually part of the function, but they just show what happens near to the value of the function as it nears values that are undefined for tan of theta. So let's have a look. So I'm going to generate the graph of tan. Remember that the value of tan is read off this tangent line here, and it's the distance from, or the height of the tangent line above the x-axis. So I'm going to move the angle button. And as you can see, the angle is starting to increase and the tan value is increasing as well. So when it starts at 0, if we go back down to 0, you can see that the tan value of 0 degrees is 0, and then it increases slowly and then very, very steeply as it gets to pi on 2 or 90 degrees, where the line is actually parallel to the tangent line. So this line here, when it's perfectly straight, is parallel to the tangent line, and so the two lines don't actually cross. And so that's why you have an undefined value for tan of 90 degrees or pi on 2. When we swing around past 90 degrees, we read our tan angle from the point on the circumference through the centre back down this way. You can see the faint line down here, and so the tangent value is really, really big at this point. And as we continue to move it around, now it starts to appear on the graph, and you can see that it actually starts from negative infinity and comes up as the angle increases from 90 to 180 degrees. At 180 degrees, or at pi radians, tan value is 0. So it goes from this point on the circumference through the centre across to the tangent line, and it's 0. So we've actually completed, you can see that the graph is at the same point, and as we continue on with our graph now, we've actually completed one period, and it will start to repeat the graph. Can you see it's repeating the same pattern of the graph until it becomes parallel again at 3 pi on 2, and then it comes back up from negative infinity back up until it's at 2 pi. So you'll notice the graph, when it drew, didn't draw in any asymptotes, it just drew the shape of the graph. And that's the same with our graph on our CAS calculator. So this is a slightly modified picture. I've just written on some of the values from a CAS calculator, and you can see again that this is the tan function, but there's no asymptotes appearing. So the asymptotes don't actually belong to the function, because the function, the actual line itself, shows you the values of tan for particular angles. And at the asymptote, there is no value of tan. So the asymptotes right down here at the bottom show the behaviour of the graph. They're not part of the function, but we do include them when we draw them. So if you're asked to draw a tan graph, you need to include your asymptotes. They need to be dashed lines, and they need to have an equation. So even if there was an asymptote along the y-axis, we would still draw it in as a dashed line, and we would still label it. And so looking at our values of tan, so our possible y values for tan of x, our maximum value is infinity, our minimum value is minus infinity, so that our range is in fact real numbers for tan. The same as with our sine and cos functions, the average value, the mean value of the tan function is this point here in the middle. If you added up all the values below the x-axis and added up all the values above the x-axis, they'd cancel each other out. So the mean position of this graph, the average value of that function, is 0. And its domain is the length that it takes to repeat from one cycle. And the easiest way to see that is either from where it crosses the x-axis to where it crosses the x-axis, which is, in this case, pi, or from one asymptote to another asymptote. That is also a distance of pi. So the period of our tan graph is pi. Now our domain is all real numbers except for where those asymptotes are occurring. And those asymptotes are currently occurring at odd numbers of pi on 2. So the number at the top is an odd number times by pi over 2. So to write that, we actually write 2n minus 1 to make an odd number of pi over 2, where our counter, our n, is an element of z. So for our sine and cos graphs, we looked at whether they were odd or even functions. And so we have two definitions for odd and even functions, and we'll see what tan is in just one sec. So if to determine if a function is odd or even, we look at what you get when you substitute in a negative value for x and what the related function is. So if you take f of negative x and your answer is negative f of x, then what you have is an odd function. And if you have f of negative x, and when you substitute in negative x and work it out, you get f of x, what you have is an even function. Sine is an odd function, and cos is an even function. So let's have a look at what tan is. So let's have a look at what happens when I find tan of x up to that white point there. So that's the length of tan x. If I take the same x distance but I make it negative, then the distance down to the line there is tan of negative x. Now I want to compare tan of negative x with tan of x, so the two purple lines. So if I take the length of tan of x and I turn it round and I slide it across, what you find is that you have tan of minus x is negative tan of x, which has the pattern of f of minus x is negative f of x, which means that tan is an odd function. Sketching graphs of transformed tan functions like the one that I've got here, a generic one that I've got here, follows the same pattern, the same process as what we used for sine and cos. So we take our standard tan graph that I've got here and we're going to select 5 points that we're going to track. Now, it seems a little bit weird, the 5 points that I'm tracking here, but I'm actually tracking one period. Okay, so we start at the one end of a period and finish at the other end of a period. So filling in this table starts with 0 and the period of tan of a tan graph is pi, so pi goes in here. Then the one in the middle is halfway between the two, pi on 2. And then I'm going to track the points pi on 4 and pi on 3, simply so that I know whether I am above the x-axis or below the x-axis for my graphs. The other thing that this is going to give us is a formula that's going to tell us where all of the asymptotes are for the graphs. So the asymptotes are starting out at pi on 2, and then we're going to shift them left and right. They don't move up and down because it's a straight line. Doesn't matter if it moves up and down, it's still a straight line. So we're going to use our transformation pattern here to map where our asymptotes are going to be. So our x dash for our pi on 2 point for our asymptote is 1 on n times pi on 2 minus b, which is going to give us a formula for our asymptotes. of 2k minus 1, so this is going to give us our odd number, and the k is just going to be our counter to generate all of our asymptotes. So an odd number of pi 2 over n, where n is our dilation factor up here. So our n is this n here, minus b as part of our formula as well. So you can either remember that if you like, or you can just generate them by continuing on the patterns out this way.